Alright, so I am back again. And this time I'm going to be talking about fusion and the main sequence. Okay, so once a star begins hydrogen fusion, it's going to join the main sequence. And it's going to spend around 90% of its life in main sequence. And as I said before, hydrogen is the fuel of the star. And at some point, under the high pressures and temperatures of the core, these hydrogen atoms are going to begin to smash together, undergoing fusion, and then they're going to form helium. Okay, so in stars, there are two types of fusion. The first type is called a proton-on-proton chain reaction, and is what occurs in most main sequence stars. And the other type of fusion reaction is called a CNO reaction, and that's what happens in stars about 1.3 times the mass of our sun. And CNO reactions are going to be talked about later by Max after this. Okay, so a proton-on-proton chain reaction is actually a little bit misleading of a name, even though it is what it sounds like. So the reaction is proton on proton, so protons are hitting protons in the reaction. And basically it takes lots of hydrogen nuclei, and within a few steps it turns them into helium. But the confusing part about that is that it's not really chain reaction. So you think of a chain reaction kind of like maybe a fission reaction, where the neutrinos that are being sent off from one breaking nuclei goes and hits into another nuclei and then triggers a reaction, which triggers more reactions. So it's not really like this, but it is a chain reaction in the sense that the final product of one little chain is going to start the next chain. So it's like each reaction is linked to the next. Okay, but enough about pedantics. Okay, so the reaction the reaction starts off with two hydrogen cations, which are literally just protons. And these protons slam into each other, and then they fuse. So they go poof, and then fuse. And then we have two protons stuck together. And then, through the weak nuclear force, one of these protons is going to emit a positron, which is carrying that proton's positive charge, and a neutrino, which carries a little bit of that proton's energy. And then that proton transforms into a neutron. And then we have a deuterium atom. So we have one proton and one neutron. Okay, so that deuterium atom continues on the chain. So another proton is going to go fuse with that deuterium. And this is going to create a helium-3 isotope. And in the process, it's going to emit a gamma ray. So that's going to be two protons and one neutron this time, plus a gamma ray. Okay, so two of these helium-3 nuclei are then going to fuse and create the helium-4 isotope, which is the helium that we find on Earth and that we put in balloons and everything. And in that process, if you think about it, it's going to be a total of two helium-3, so that's 4 protons total, plus 2 neutrons. So we only need 2 neutrons and 2 protons, so it's going to shoot off 2 of those protons. And those 2 protons are going to be what begins the next cycle of this reaction. Okay, so basically hydrogen turns into helium, this produces light and heat, and this fuels the star. And so this fusion is the force that counteracts the star's gravity and keeps the star from collapsing inwards. So the pressure of layers of stellar matter weighing down on any given point within the star are counteracted by the thermal pressure, which pushes upwards, created by the fusion reaction. Okay, and so this counteracting pressure, as I said, it takes the form of light, neutrinos, and heat. And this, in total, plus the gravity, creates what we call the hydrostatic equilibrium, which is a balance between gravity and fusion. And this equilibrium keeps the star the size it is. So we have one force which is pushing outwards, trying to explode the star, and one force, gravity, which is going to be pushing inwards. And those are at a balance, and they're going to create and keep the star the size that it should be. Okay, and so a star is going to spend around 90% of its life like that, which is around 10 billion years for stars around the size of the sun, which undergo this kind of fusion. And during this time, they're going to experience very little change. So there's not really anything that's going to happen to them. They're just going to sit there and they're going to go through their hydrogen, and they're not going to change size, they're not going to change color, they're just going to float around the galaxy wherever they are. Okay, and basically what's going to happen eventually is that the hydrogen in the core of the star runs out. It's going to lose equilibrium, and it's going to fall off the main sequence. And so Max is going to talk about what happens then. All right, thank you.